Hi, my name is Morgan Fine-Morris. Today I'm presenting learning decomposition methods with numeric subtasks. So hierarchical task network planning uses decomposition methods, which are encode hierarchies of preconditioned task-subtask relations to decompose tasks into simpler tasks until finally they reach the level of plans of primitive tasks. And some cognitive systems like Icarus use hierarchical structures to represent domain knowledge and plans. So it's useful to be able to learn the decomposition structure from something like a plan trace. For those unfamiliar with decomposition methods, I have an example. This is taken from the video game Minecraft. So if we have this task to make a crafting table, that we can decompose it into making planks, which are used to make the crafting table, and then crafting the crafting table. And the decomposition method looks something like this, where we have the head, which is the make craft table task, and then preconditions and subtasks. And our preconditions specify that we can only use this, we can only decompose the task into these two subtasks when we don't have a crafting table and we don't have any intermediate resources needed to make it, but it is possible to gather enough wood from the world to make the intermediate resources and the crafting table. So unfortunately, acquiring decomposition methods is very expensive, and it needs to be done either by a human expert, or it needs to be learned by an algorithm like the one I'm going to present today. The algorithm is called trace to numeric, and it learns decomposition methods for domains with numeric preconditions and numeric subtasks. And it estimates it to learn the structure of the domain. It estimates something that we call domain landmarks to detect end of subtask states, which it uses to infer the end of subtasks from the training traces it's learning from. For those who have never heard the term domain landmarks, it's basically like a planning landmark, but it's applicable to more than one type of problem or problem class in a domain. I'm going to compare 4 different policies corresponding to 4 different method sets of learned numeric methods. And I'm going to use those policies to compare the following, to make the following comparisons of flattened structure task networks versus very right recursive structured task networks. Task networks learned with landmarks versus without landmarks, and networks learned with custom or hand selected landmarks versus algorithms learned versus hierarchies learned with algorithm learned landmarks. And you can see in the table on the right, we have the policy names and their various characteristics. We expect that we're going to find that our right recursion creates methods that are more flexible, but also more expensive to use, and that landmark learning does provide speed up during planning, and that the custom landmarks are still better than the learned landmarks. Oh, and I should add, for those familiar with HTN Maker, the RR policy, which has no preconditions and is mostly right recursive, is similar to the methods learned by HTN Maker. The domain I'm going to use is called Lightcraft. It's a simplified crafting domain based on the crafting system of Minecraft. There are 2 types of actions. The craft action consumes items to make new ones, and the gather actions transfer resources from the world into the agent inventory. And these actions have exclusively numeric effects, so they operate by incrementing and decrementing counters in the state. And therefore changes in the numeric variables indicate the boundaries of subtasks. Also, the domain is partially ordered. We have an example trace here on the right. And you can see the fluctuations below in the amounts of resources as we proceed through the trace. And here's a possible decomposition for that would reproduce this trace. But it's only one of many possible valid decompositions. The policies, I mentioned that our policies are going to compare the performance of different types of hierarchical structure. Two of the ones that we're going to look at, which both take advantage of landmarks to form the structure, are shown. Examples are shown on the left. The first one has a flattened hierarchy, and the second has a right recursive hierarchy. You can see that both are using, for method M1, using a landmark. The value agent Planck's is 4 to decompose as the leftmost subtask of make craft table. And the primary difference between these two structures is how the M1 method decomposes its rightmost subtask. In the first structure, we decompose directly into the primitive task, and in the second structure, we need another method in order to decompose, in order to get to craft blanks. It's not particularly obvious here because these are small examples to fit on the slide, but for larger problems, the right recursive components of the decomposition can get much larger, but it's difficult to fit that on the slide, unfortunately. We're also going to be looking at another type of structure. The RR structure that I mentioned is similar to the one used by HTN Maker, or learned by HTN Maker, where we have always have a primitive left subtask and a compound right subtask until we reach the final subtask, of course, or until we reach the final action of the trace. And these different structures respond to an increase in the number of actions in different ways that can impact their performance when a planner is using them to generate a plan. In the case of the first structure with the flattened hierarchy, typically we'll see an increase in the average number of subtasks, but not in the decomposition depth or in the number of methods learned, or at least less in terms of the number of methods learned. Whereas for 2 and 3, there will be an increase in both decomposition depth and the number of methods learned, and that can mean that the HTM planner plans more slowly because it possibly has to check more methods preconditions to find an appropriate method. So in addition to looking at different structures, we also designed these experiments to test whether or not a modification made to the numeric preconditions, to our numeric precondition learning system works. The update was necessary to work with the numeric subtasks, which wasn't in previous versions of the system. So I'm going to work through an example, so hopefully to explain it. So if we have this make craft table trace, and we already know that the landmark is the value agent Planck's is 4 fact, and we're trying to learn a method M1 from the previous that I mentioned in the previous slide. Typically, we would just get the actions that precede the landmark and unify them so that their state variables are named the same, so that their state variables are named similarly, and then we would use a combination of goal regression and function composition to essentially concatenate their preconditions together. And this is enough to make sure that we don't apply the decomposition in situations where it would be impossible, but it isn't really enough to determine whether or not these preconditions aren't enough to determine if it's a good idea or useful to apply this decomposition. So we made an addition to the learner that lets it infer certain facts, infer new preconditions from the context provided by the initial state of the trace. So you can see that the agent Planck's counter is 0 in the initial state, so we can infer that and insert it into the preconditions of this method. For the experiments, I selected a set of craftable items of a sufficient complexity to serve as our tasks. So for the training problems, we had 10 problems per task. And for the test problems, we had 4 problems per task. And for all of these, the initial state was randomized so that there were random numbers of resources in the world that the agent could gather, but the agent had to start with an empty inventory. We used an HTN planner to generate the training traces. And then we learned methods using our algorithm under these 4 policies from the training traces, and tried to solve our test problems with them. We find that generally landmark selection can impact task solvability because the easier tasks are not covered by the LL and LLRR policies, but CL and RR are able to solve tasks of every type. However, we don't, as you can see, like across the policies for a given task, there really is rarely variation in the plan length. So we infer that there's little impact of hierarchy style or landmark choice on plan length. And also note that the RR policy with which had the deepest decompositions, didn't necessarily produce inefficient plans. It's arguably the best policy from the perspective of plan length, because it both solves all the problems and also doesn't have any upticks in the number of actions needed to complete the task the way like CL does. If we look at planning duration, however, RR is much more expensive than the others. In the graphs below, the problems are ordered roughly from easiest to hardest. And we compare them with the planning duration in seconds. And you can see that RR tasks solved by the RR policy, problem solved by the RR policy, have this little tail at the after problem, starting around problem number 20, because it has a hard time solving the harder problems quickly. Comparatively, the others are flat. If we zoom in to the 0 to 4 second interval on the bottom, in the bottom row of graphs, we can better compare CL and LL and LLRR, and we can see that LL and LLRR do surprisingly well. LL is probably the most time efficient of 3, and LLRR is fairly competitive, with CL, well, better than CL, even if it's easier problems, even if its solving of the easier problems is slightly slower. But I've circled the problems where we had those longer plans in the previous slide in red, and the problems that required backtracking are in blue. Most of these problems did not require backtracking, which suggests that we're learning appropriate preconditions. But this one set of problems for these 2 policies did require backtracking, which suggests, which coincides with the increase in the amount of planning time that they needed. Yeah.
Hey, Morgan, this is your 2-minute warning.
Okay, thank you. So there's been some previous work on this. Dr. Langley learned hierarchical skills using example problems and user-provided concept hierarchies for Icarus. And HTM Maker in 2016 uses traces and annotated tasks to learn methods of a similar style to the RR methods that we tested. but both of these require some knowledge engineering beforehand, and we're trying to cut down on how much knowledge engineering we have to do. Word to HDN does cut down on the amount of knowledge engineering, but their preconditions can only, and while they do learn numeric preconditions, they only learn simple arithmetic. So we're trying to increase the complexity of the numeric preconditions we can learn, which brings us to trace to numeric, the predecessor of trace to numeric, which was not named, went unnamed. And it took in traces in a set of possible domain landmarks to help guide it, to help it discard inappropriate landmarks. And it learned numeric methods with numeric preconditions, but it wasn't capable of learning numeric subtasks. So that's an addition that we've added for this work. In conclusion, all the policies we looked at, all the possible structures had their strengths and weaknesses. The RR policy was slow, but produced shorter plans and solved all tasks, whereas LL and LLRR were faster, particularly for harder problems, but failed on easier ones. And CL had performed well for easier problems and solved all problems, but started to run into trouble, started to slow down for harder problems. So in result, we've confirmed our intuition that the right recursive hierarchies are slightly slower, but generally are more flexible. But also found that surprisingly, the landmark learner, while it's selecting unintuitive landmarks, it is selecting effective landmarks, at least for the harder problems, than the custom landmarks that were handpicked. Okay, that's all I have for today. I'd like to thank the Naval Research Laboratory, the Office of Naval Research, and the National Science Foundation for providing funding for this research. And I will take any questions.
Wow. Hey, Morgan, I'm glad you're continuing to work on this problem. I think it's an understudied problem that deserves a lot more attention. The one thing that I did not get from your talk is to what extent the learned methods are generalizing to new problems, in particular to more complex problems of the same type. That's what you want from any kind of plan learner, including HDN learners. Is as you train it on some problems, and now you give it problems that have, say, more objects, and you want it to generalize, ideally, perfectly, so there's no search on those, but at least reduce the search drastically. I could not tell whether or not that is happening. Could you just talk about that a bit?
So I do think that is something of a weakness. I don't think it can generalize to like never seen before final products. I do think
I'm not hearing you very well.
Oh, okay. Can you hear me now?
Go ahead.
So it can't generalize to never before seen final products, but it can generalize in terms of like if the number of like numeric the numeric values of the resources change, it can generalize there. So I think I decreased I allowed the test problems
okay, so
you have smaller numbers of resources.
So you're generalizing over numeric values, but not over problems that are structurally different, even if they could be viewed as elaborations of more basic problems.
Yeah, I think
okay. So similar to the same issues that HDN Maker had.
Yeah.
Okay, that's fine. I got it. Anyone else? No. Be nice.
I'm always nice. I was wanting to know whether the algorithm that you've developed here or used will also be useful in a hierarchical goal network to learn those kinds of methods to decompose, decomposition methods in HGNs.
Yeah, I think it can be applicable to both. And we sometimes sometimes like talk about it as an HGN learner instead of HTNs, although I think there would need to be some tweaks made to make sure that it's actually, I think there'd need to be some tweaks made to make sure that it works properly for an HGN, but I don't think it'd be too difficult to make those tweaks.
Okay.
So yes.
So we'll take one final question from Slack from David. So how much variation were there in the traces? For example, for making an axe, the agent has a choice to build the handle first or the blade part first. Can your HTN learner handle learning these decompositions while considering these variations?
So we did try to maximize the amount of variation that we did try to maximize that sort of variation in the plans. But I don't remember off the top of my head, like the handwritten methods could, I think, construct traces like that, but I don't remember off the top of my head if it actually did. So I could check that and potentially get back to you, but yeah.
Okay, thank you. Let us thank our speaker one last time.